Harmonic analysis involves many decisions, not least of which when chords and keys change and what they are. In automated context, these tasks can be handled separately, and it would be useful to have clear benchmarks on the relative importance of each. For instance, how accurately can we determine what chords are, knowing already where they change, using a simple profile matching approach? Profile matching involves comparing the usage of pitches in a source, either audio or symbolic, with a prototype for expected behavior. Often a binary profile is used, with 1 for membership of the key or chord and 0 for non-membership. The profile matching approach brings many advantages, though there are some issues with the simple binary prototype. For instance, it doesn't do well in handling the various forms of minor key. It also makes no distinction between the relative prominence of different scale degrees. For instance, we may wish to afford special importance to the tonic and dominant scale degrees. Craig Sapp proposes a modified form of the binary prototype for this reason, and further refinement is to be had from the empirical studies coming from psychology, from Krumhansel and colleagues, and from corpus study, as shown here from Quinn and White. These typically perform better, and our paper discusses some cases relevant to the current study. These empirical prototypes bring not only improved performance, but greater flexibility. Though they too are limited, for instance, to build up key prototypes from a corpus of works, we need to know what the key of each of those works is in advance, and even then, many prototypes build up by assuming that the key remains constant throughout, so ignoring modulation, or else taking a semi-arbitrary segmentation of the first 8 measures or 8 seconds, for instance. Prototypes built from human analyses stand to improve this situation further. We can take a score or audio source, divide it up into all of its chords and keys, and we can build highly context-sensitive prototypes from there, for instance, for the major chord as used by a single composer in a specific genre style. Finally, because we won't always know in advance where the chords and keys change, we need to know how robust these methods are to small errors in the segmentation. Let's return to this task of key matching and consider the Quinn and White profile in the Beethoven audio case in particular. We can compare the performance on the correct segment with performance on segments that are too long and too short, and we can also systematically vary where that change is made, centering it, positioning the change at the end, and at the beginning. And we see some interesting asymmetries in the results that come out. Thank you for watching this video. For the code, the profiles, and around 100,000 chords worth of analysis, please check out this repo.